Okay, so in the early 20th century, one of the leading discoveries that really led to chemistry becoming a modern science is the avogadro to study gases. And among the things that were done was a contribution by Amadeo Avogadro, who recognized that for a sample of gas at a constant temperature and pressure, the volume of that gas is directly proportional to the number of gas molecules. Or another way to say that is that the volume of a gas at a constant temperature and pressure is dependent on the number of moles of gas. So the volume is proportional to N, the number of moles. Okay, and what this basically says is that if you have some sample of gas under some pressure, say it's in this piston right here, if you double the number of moles of gas, you basically double the volume of that gas. And this makes quite intuitive sense, right? You put more gas molecules inside your container gets bigger if it is able to expand. So think of a balloon. If you put air into a balloon, it gets to some volume. If you continue to put more air into the balloon, your balloon will get bigger depending on how much more air you put in. So this is a fairly straightforward idea. And again, this proportionality between volume and the number of moles is known as Avogadros Law. And in fact, it leads to something that we call the standard molar volume. Okay, that is allows us to basically count gas molecules in terms of the number of moles of molecules by a volume of gas. So rather than having to weigh a sample of gas, we can simply measure the volume of that gas and understand there's this relationship between the number of moles and the volume of that gas at a standard temperature and pressure. So this allows us to identify equal volumes of gases, recognize that equal volumes of gases will contain equal numbers of molecules. And if we define a standard set of conditions that we call STP, which stands for standard temperature and pressure. Okay, so STP. This is standard temperature and pressure. We can define a sort of standard set of conditions that somewhat arbitrarily means the temperature is 0 degrees Celsius, that's 273 kelvins, and the pressure is defined as 1 atmosphere. So if we are at STP, it turns out that any gas, whether it's helium or argon or carbon dioxide or oxygen or anything, or sulfur hexafluoride, all of these gases occupy the same volume for the same number of moles. So if we had 1 mole of any gas under these conditions of STP, standard temperature and pressure, at 0 degrees Celsius and 1 atmosphere of pressure, all gases will occupy the same volume, which is 22.414 liters. So this is what we call the standard molar volume, the volume of any gas, of 1 mole of any gas at STP. So this is a pretty useful relationship because at STP it's very simple for us to relate the volume and the number of moles. So let's say we have a sample of helium gas, and this gas occupies a volume of 155 liters at STP. Again, it really doesn't matter what gas we're talking about, but in this case we've got helium. So we can calculate the number of moles using this standard molar volume, the volume of 1 mole of a gas at STP. So we're going to use this value. 155 liters is our volume, and again our standard molar volume is just a conversion between moles and volume. So we say that 1 mole, in this case of helium, occupies a volume of 22.414 liters at STP. And it's important here that we are understanding that we're at standard temperature and pressure because this relationship really only holds true under these conditions. Okay, so under these conditions we have 155 liters, so we'll grab our calculator here. and we'll say 155, and we'll divide by that standard molar volume, 22.414, telling us we have essentially 6.92 moles of helium. So here we have 6.92 liters, or excuse me, moles of helium. So again, it doesn't matter what gas we're talking about. This could be moles of nitrogen gas, or moles of argon gas, or moles of sulfur hexafluoride, or oxygen, or acetylene. You pick your favorite gas. They will have the same volume. However, if we were then to ask, what is the density of this helium sample? Okay, again, it really doesn't matter in this case. All that really matters here is that we're at STP, but we can calculate the density in grams per liter by using the molar mass here, 6.92 moles of helium, and we look at our periodic table and see that 1 mole of helium gas weighs 4.003 grams, so we will say 6.92 moles of helium. We could make it simpler, but we're going to just do it this way, times 4.003 grams of helium per mole. That's our molar mass, and we'll divide that by our total volume here, 155 liters, telling us that the density of helium at STP, the density of helium at STP, if I can find my thing, is 0.179, running out of space here, grams per liter. Okay, so that's one sort of simple application of these standard molar volumes. We can very easily calculate densities of gases at STP. Okay, again, the volume and number of mole relationship does not depend on the type of gas we're dealing with. So whether this were helium or neon or acetylene, it would always be 6.92 moles of helium would occupy 155 liters at STP. And we can use the identity of this gas now to calculate the density of the gas at STP.